right, welcome back. Hopefully you are all caffeinated and ready for a high-powered series of talks. It's with great pleasure that I'm excited to introduce Alex Rodriguez. Alex is an assistant professor here at the University of Michigan in the Department of Computer Science, whose work develops AI methods for modeling complex spatio-temporal dynamics that enable trustworthy, data-driven decision-making. His research spans machine learning, time series analysis, and uncertainty quantification, and critically, AI for science, with applications to population health and engineering. So we're excited today to bring Alex to our kickoff for the second session. And with that, I'll turn over to him as soon as the slides show up.
So I will discuss today about how we can integrate AI and scientific models, how we can see multiple ways they can complement each other of these two modeling paradigms. And the application that we'll be mostly talking about is in health. So in health, we have one big component that in machine learning AI we have been discussing multiple times, like multimodal data. And I have been looking into epidemiology. So we have multimodal epidemic data coming from multiple sources. We can see the first panel in the left, behavioral data. We can see also genomic data, environmental samples from wastewater, and so on. And we can see how this is an input to our predictive modeling in the middle one, and then how we use these predictive predictions in decision making. And in other health domains also, we can think of similar pipelines and similar data sets, multimodal data sets in, for example, computational biology, clinical informatics, and drug discovery. So one big component is data. Another component of my talk is scientific models, how we can bridge this AI data and scientific models. And if we open this book on epidemiology, we will see, broadly speaking, two types of models that we usually refer to as mechanistic models in epidemiology. One class of models are based on differential equations, ordinary differential equations. This is the popular SIR model, which S stands for susceptible, I for infectious, and R for recovered. And essentially, we will have some people in each compartment, and these differential equations is telling us how many people are moving from one compartment to the other, modulated by these parameters beta and delta. And we have initial conditions data. We can fit these models and also see the evolution of an epidemic. And on the other hand, we have agent-based models, which are simulations, computational simulations that are developed by some experts. And they essentially here, the agents are people, and they will be interacting in a computational world in different settings. As you can see here, we have a workplace, we have a household, we have a school. So we have these scientific models in epidemiology that they have been created by experts. They are not perfect. They have some deficiencies, but they encode some causal mechanisms that could be relevant for many inference and predictions. We also have been exploring or working with pharmacological models, pharmacokinetics, and pharmacodynamic models. These are ordinary differential equations. This is a diagram that describes the variables that these models may have. In this case, we are looking into dexamethasone dose for COVID-19, for essentially in a person. The dexamethasone goes to the plasma, then goes to the lung. You can see that goes to the immune response, and in here in the immune response, there will be some interactions with the viral load. And these are below, there are the differential equations. And if we had also some parameters and initial conditions, we can simulate this, the dynamics. So these are models that are there, have been used and there are some benefits from them. And in my work, we are trying to connect them with AI. And one of the main motivations is that scientific data is scarce, and the possible problem instances are many. And we call this in machine learning data sparsity. And if we see these two dimensions or axes, we have data in one and the scientific knowledge in the other. We can, in the extremes, for example, in small data and lots of scientific understanding, we can find pendulum kinematics. In the other extreme, we can find language modeling. And in the middle, where we have some data and some scientific understanding that is imperfect, we have biology and health problems, and also other domains. For example, weather prediction can be one here. So we are thinking of how we can complement these scientific models with AI. We can think of how first scientific knowledge can help AI, and it can help us to identify some solutions that are not consistent with theory or with at least some well-known facts. And also, it can help us, and I am especially interested in this question of how it can help us to have machine learning AI systems to answer what-if questions. What-if questions that we're going to be developing a little bit more on this. And the other side of the coin is how we can make AI help these scientific models. Scientific models are well known for not being able to incorporate some multimodal data. It's hard for them to understand. It's hard for an expert to understand how this multimodal data connects with the variables that they have already in their models. And in addition, calibration of these models can be complicated and cost prohibitive because there are some expensive simulations that are out there. So we have these two aspects, and I will be addressing in our solutions these two aspects. We call these science-informed AI frameworks that we have. And we have two ideas. One is incorporating dynamics of these scientific models. In this case, we have the SIR model. We want to extract some relevant signals to inform the machine learning model. And the other idea that I'm going to be discussing is how we can help a scientific model calibration with neural networks. And here we are going to be seeing the backpropagation part because we are going to have a differentiable simulator of the scientific process. So let me go to the first idea. The first idea, I will be explaining a specific application on counterfactual prediction in complex dynamical systems. As I said, I work with epidemics, and this is an example, from motivating example in epidemics, where we have, as a present time, we have observed some epidemic curve, and we have observed also what was the policy that was implemented during that time. And we can also ask the question of what could have happened if I had done perhaps a stricter policy or a more loose policy. You can make predictions for that. And on the other side, you can also ask the question for the future. What will happen in the future if I keep doing my current policy, or if I change my policy for something else? The decisions here, of course, policy, but we also want to understand some aspects of this time series because we may want to do some logistical planning. We may want to understand when we are going to be seeing the more number of deaths or cases or hospitalizations, so then we can prepare our hospitals. So predicting the time series itself is important for us. And we have also some challenges that arise from these very complicated problems. First is scarce observational data. We only have data that we are observing across the country and even across the world, but there are different. But this data is not like every single place applies the interventions in an ordered manner. Right? There are some nuances of how people have making decisions across the entire country. Also, we have multiple compounding factors. Also, we have selection bias on the intervention application, and we also have time-varying interventions. So we have multiple challenges here, and in my work, we have been working first in the counterfactual prediction side, and understanding the past, understanding what will have happened in the past. We also looking forward in future work to look into the future, and specifically addressing the challenge of scarce observational data. So I'm going to be focusing in explaining an idea that is going to be addressing these two components. Our proposal, we call it knowledge-guided causal inference, where, as you may remember, we had these mechanistic models that are going to be useful for encoding causal mechanisms. They are indeed the gold standard when you are making what-if questions, but they are incomplete and misspecified. On the other side, we have generative modeling, which we have that is strong in time series generation. It can do it in a very detailed way, and it can integrate multimodal data, but it doesn't have causal mechanisms, and also it is data hungry. And we want to have something in the middle that where we call knowledge-guided generative model for causal inference, where we are going to be bridging these two. So how do we do it? We are going to be illustrating that intuition with an example. The question here we have is what could have happened if we had a stricter policy? And what we see, this is data that we have generated through simulation. One of the challenges of working on these questions is that you don't have ground truth data for the counterfactual, because the factual is what didn't happen. So we have data for only the factual, the observed data. And we can, using a simulation, we can get the counterfactual one. In this case, it's a more strict policy. So what happens when you train a diffusion model in multiple cities of this time series that it only observes the factual data? And factual data, just to clarify, there are multiple cities. Some of them have implemented the policy, others didn't implement the policy, so the diffusion model can learn from this. The diffusion model indeed doesn't learn well sometimes. And in this case, it didn't learn that for a more strict policy, the expectation would be that the mortality rate would be lower than what the factual data said. So this problem, we were asking ourselves, can we facilitate this or fixing this problem by using a mechanistic model? And this indeed, there is something we call counterfactual relationship between the factual and the counterfactual, which this mechanistic model is going to be helping us to capture. So you can see this counterfactual relationship is essentially moving the peak or the shifting the time series a bit to the left and also going down. And what we observe is in the mechanistic model, even though there is a large error, and here the mechanistic model predictions are the ones that are dashed, and we can compare against the ground truth, which is the solid lines, there is a significant error in their estimates. However, even though the error exists, this counterfactual relationship is still at least resembling the actual counterfactual relationship in the ground truth data. The diffusion model, we're not able to capture that. So we are thinking, our hypothesis is that by incorporating this counterfactual relationship from these mechanistic models, we can improve our diffusion model in getting to a better solution. Now, the one challenge here is that we don't know how much we should rely on this mechanistic model. Mechanistic model, it will essentially will give us some information about the direction we should be moving the time series, and also how much we should be moving it, but we don't know how much to rely. We know that it's imperfect. So in knowledge-guided machine learning, for the people that are aware of that, you will learn this weight of how much to rely on the mechanistic model based on validation data because you have observations. But in counterfactual case, you don't have these observations. You don't have a good validation data. So what you have to do is we have to create a new heuristic algorithm in order to identify this guidance and strength. And in order to enable us to do that, broadly speaking, we aligned the data that we observe, the factual data, with the mechanistic predictions. And then we find the maximum correlation, the guidance and strength that is going to be giving us the maximum correlation between the diffusion model and also the mechanistic model. So by doing this, and this is maybe an illustration of how this will look like with COVID-19 and the dexamethasone, we can see that we find the correlation, and nu is the guidance strength. We find the guidance strength that maximizes the correlation, and then we use this in the test set, and we find that actually it is very close to the lowest error. What's the distance and RMSE are error metrics, so we want to minimize it. So if we get these new values from the correlation side, we can apply them in the synthetic test set, and we find that actually it's very close to the optimal error. So this is a way to get to this guidance strength. And what we did in experiments is we generated data using some sophisticated, you can see, times ODEs, and we use a more simple ODE in order to inform our diffusion model. And now going back to what we have seen in previous slides regarding to this diffusion model, now what we are incorporating this guidance, knowledge-guided guidance, now we can fix this problem, as you can see here on the right, how now it is maintaining the counterfactual relationship that we wanted to maintain. And we do also experiments in multiple cities and multiple essentially patients in the dexamethasone case, and we also obtain some results. And here I want to emphasize that the expert ODE is the mechanistic model by itself, and you can see that it has a large error. But even though it has a large error, the guidance that it provides regarding to the counterfactual is useful, so that we are bringing it to the diffusion model and is taking advantage of it very well. And the second part of my talk is about now looking into neural calibration of agent-based models. Thank you. And now here we are looking into a scientific model that we are going to be converting it to a differentiable scientific model. In this case, it's an agent-based model. An agent-based model, I had already illustrated it. It has some networks. It has a process of transmission of disease, and also it will be a progression of disease. And what we are going to be doing, and I'm going to be discussing in a moment, is we are going to be making this differentiable because we want to connect it to a neural net with a neural network. This neural network will help us to ingest some data sets that otherwise will be hard to ingest in this simulation model, and then make predictions about the parameters of the simulation model. So, so number one, we are taking advantage of the data sets. In number two, we are simulating for multiple days. And number three, we are aggregating those results, comparing it with ground truth data, calculating a loss function value, and then doing backpropagation because we can, because everything is differentiable, we can backpropagate through the entire pipeline. So that is the idea that we bring to here to the table. One, the main idea is the differentiability in the agent-based model. Differentiability in the agent-based models is kind of a new concept, and indeed, differentiable simulations are available also in other domains also. This is a domain in epidemiology where we have brought this idea of agent-based model differentiable. And what we have to do in order to enable this differentiability is to reformulate disease dynamics. We have to work, instead of working as individual agents, we have to work with a network, and then we are using what people have used in graph neural networks, which is the message passing operation. But instead of having a black box function that we are going to be approximating, we have a function that is fully specified by domain experts. So we are taking this function from epidemiologists that have been working on this domain, and we are just using it and calculating the probability of a person being infected after the interaction with other people based on the multiple features from the people that are interacting. Once we have this probability, we have a stochastic process. We are going to be sampling from this probability. And when we are sampling with this probability, we are essentially doing a Bernoulli sampling. And if you're familiar with sampling in machine learning, specifically end-to-end pipelines, it might break the differentiability, might break the gradient propagation. So what we have to do is to rely on some tricks that have been developed for variational autoencoders, that is the reparametrization trick, in order to approximate this sample and then do backpropagation through this Bernoulli sample. And finally, I want to talk about why we care about incorporating neural networks in the calibration of a scientific model. Because we can help us to approximate better the joint distribution of the parameters. It's a joint distribution of the parameters is going to be a complicated function. And if we have a neural network, it's going to be helping us to navigate through this solution space in a more effective way. Second, that is help us to ingest these data sources that otherwise we will not be able to ingest, and help us with identification of the parameters. And third, we can use the same neural network in other locations and take advantage of some transfer learning across multiple locations, and we can have a more robust neural network for that. And learning to calibrate is as simple as just update the parameters of the neural network, and then with that, you're updating the parameters also of your agent-based model. So we did experiments in COVID and influenza here, and the takeaway from these results is that it leads to better calibration. Better calibration leads to better predictions also in short term, and also different. Also, we were thinking of how we can apply this to policy. We found that by having a better calibrated model, you can even have a different recommendation in policy. Some concluding remarks So we have in this, today I have been discussing mostly about this, how we can connect AI with mechanistic models. In my work, we also have other methods that are more on the data-driven side, and specifically we have been looking into spatial temporal propagation, multimodal uncertain quantification, and also even looking into data quality issues like data revisions. We have also some work on uncertain quantification, of how we can make sure that we are able to adapt to distribution shifts, and it's an important problem indeed, because we are participating or helping the CDC in forecasting challenges, and it's important to provide certain quantification that is well calibrated. So we have some work on that space as well, and we have been working on multiple fronts on doing surveys and tutorials. So I will invite you, if you're interested on participating in this community, invite you to connect and learn more about it. Some concluding remarks I want to say is that I show you today some AI plus science methods that will help us to make more accurate predictions, that it will help us to also, for machine learning, to learn in a more efficient way and to answer also what-if questions. So these are my details, and I look forward to any questions that you may have.
kick us off with one question, though. So, Alex, one of the things I really liked about this is that in the agent-based model you were talking about, the way that it's trained isn't just purely machine learning. They're actually building in experts to think about that error function. And I was wondering if you could speak to, in the AI and science space, how easy it is to translate the expert wisdom into those kinds of functions. Like, what sort of process is it? How easy is it to find collaborators in that space? What is that like exactly?
It's an excellent question, David. So I didn't present this today, but we have also other collaborations, specifically with civil engineers and also with also people in aerospace working on differentiable simulators on their domains. So they are really excited about the possibilities that opens this. So I'm not sure if it is super easy, but at least I was able to find them. And then they are very excited about the possibility of creating these differentiable simulators and seeing how they can be complemented with machine learning.
Great. Thank you so much, Alex.
Yes,
We can bring our next speaker up. Right. I'm thrilled to introduce our next speaker, Vivek Gopalakrishnan, who is a PhD student in the Harvard MIT program in health sciences and technology. His research combines computer vision and medical physics to build spatial models that extract 3D and 4D information from 2D medical images, improving diagnostics and image-guided interventions and surgical robotics.
All right, so the warning was this is AI plus surgery, so if you don't like blood, look away for one slide. Okay. So I think when most people hear the word surgery, you think of a scene like this. This is an example of an open heart procedure called aortic valve replacement. And in these kinds of procedures, you can imagine the surgeons are able to see and touch a patient's anatomy with their own eyes and hands. But this isn't the only kind of option that you have for these procedures. Okay, the blood's gone if you were looking away. There is actually a whole other class of minimally invasive image-guided procedures that can achieve basically the same outcomes. So what you're seeing here is X-ray guidance for a heart procedure. The surgeon, these are their hands at the bottom left, is inserting a catheter up into the femoral artery, guiding that all the way up and around the aorta, and then finally deploying a replacement heart valve. And all of this is done without ever opening up the chest. So these kinds of procedures can be a lot more tolerable for patients like elderly patients, for example, but they bring their own set of challenges. So whereas before the surgeon could see all of the anatomy with their own eyes, now all of the supervision is given through 2D projectional images of the anatomy. And so the roboticists in the room might recognize this as like an implicit SLAM problem, but basically the surgeon has to both figure out where they are in space as well as doing all of the fine motor actions that are required for these very delicate procedures. This leads to a bunch of really cool complications, or I guess really challenging complications. They're cool from a CS perspective. So in this case, what you're trying to do is fix this internal bleed in the gut on the left. And what the surgeon has to do is start at this root node in a vascular tree and figure out what branches on this highway to follow in order to get down here. And this mapping task is really, really challenging. It can take hours to figure out exactly how to get there. And if you're trying to solve something like an internal bleed, you often don't have hours. A very interesting side project that has very similar problems is in surgical robotics. So on the left, this is a surgical robot that can do fully autonomous stroke interventions. And so this is a really great advancement, but the main challenge for the robot is that all it gets are these two orthogonal x-rays of a patient's head. What you're seeing is contrast dye being inserted into a vessel at the base of the skull and then traveling around the neurovasculature. And so from these two x-rays, the robot has to figure out where it is in 3D and how to navigate a device to fix a stroke deep in the brain. So the goal of my research is to build computer vision models that are able to take all of these 2D x-rays that you commonly get during surgeries and build dynamic 3D representations that make the surgeries easier for both clinicians as well as surgical robotic systems. So this is a cool goal. You might hear this and think of stuff like reconstruction methods or more recent World Foundation models that are able to extract the physics of how the world works from 2D images. But the main challenge that is kind of pervasive in all biomedical tasks is that the sample sizes are tiny. Even if you have a really great clinical collaborator and you get 10 years of retrospective data from your hospital, you might only be able to get at most a couple hundred examples with which to train a model. And this is clearly not enough to get something that will generalize well. I think you also run up against a really interesting data limitation, which is that if we take some of these very advanced procedures, they may have only been 10,000 of them done in the world at all. And so how do you build a model that can really generalize? I think one way to just put this into perspective for the data or for the machine learning engineer is how many examples would you really feel comfortable with an AI being trained on in order for it to do surgery on you? If we sample data from every person in Ann Arbor today, so like about 100,000 patients, would you really feel confident that that model could generalize to your specific anatomy and your specific disease? And I think for most of us, the answer is absolutely not. So we need a slightly different paradigm for these biomedical surgical tasks. And so what I'm proposing is something that I call patient-specific machine learning. And in order to do this, we can actually exploit some very cool parts about the patient care pipeline that are unique to medicine, or at least to surgery. So one thing that we can assume as a prior is that every patient who comes in for surgery has some sort of preoperative volume, like a 3D CT or a 3D MRI. And one of the first things that I built in my PhD is a physics-based X-ray renderer that can take these 3D volumes and render out synthetic 2D images from any camera pose. If you're familiar with nerf work, this is basically the same rendering equation, except you can drop like the color term and the transmittance term. So X-ray is basically just a line integral of density. And what I'm showing in this GIF is the camera moving all over around the patient's chest. Even though this is like a very basic forward model for X-ray, you get very photorealistic looking results. So the top row is real X-rays from patients in a variety of different surgical specialties, and then the bottom row are synthetic X-rays that I've rendered from their CT scans. And you can see that you get very photorealistic looking results, which can be used as synthetic training data for a patient-specific model. As a key application, I want to show how we've solved one of the long-standing challenges in image-guided surgery, which is the X-ray camera pose estimation problem. So in this setting, you have a 3D CT shown here and a 2D X-ray that was acquired during a surgery. And what we're trying to solve for is the pose of this X-ray camera. For the computer vision people, this is basically like extrinsic camera matrix optimization. And so what we do here is exploit the fact that every patient who comes in for a surgery is going to have a CT on file. And using the differentiable renderer, we start by rendering a bunch of synthetic X-rays from random poses around that patient. We can then take those random X-rays and just feed them to your favorite CNN, so like a ResNet 18, and ask it to predict the camera poses for all of these models. Since the renderer that I developed is differentiable, you can also re-render poses or images from these estimated poses, and then finally feed all of this back into a single loss term. The upshot of this is that all of this training is done with purely simulated data, so you have perfect ground truth for every term of the loss. And we can train this iteratively on potentially infinite amount of synthetic data from that one specific patient who's going to undergo the surgery. And so the upshot, or like one of the cool things from this very overfit model is that even though it's trained on purely synthetic data, it generalizes perfectly to real X-rays. So what I'm showing here is an initial prediction from this patient-specific model, and then that prediction gets optimized with just a few iterations of gradient descent to get some sub-millimeter accurate camera pose estimations. And so this is the first model that can consistently get sub-millimeter accurate camera poses for any patient and for any procedure or pathology, and it's all trained using just a single routinely acquired CT scan. Real quick, I'll just go through some of the cool applications of this. This is going to be really rapid fire, so if any of this is interesting, just feel free to talk to me at the poster. But in pediatric neurosurgery, we're now able to align these 2D X-ray videos of blood vessels with preoperative 3D volumes and decode some of the fluid dynamics that's happening in patients undergoing neurosurgery in real time. Another really cool example that we're able to do now is in radiotherapy. So now we can correct for the motion of a patient when they're in a radiotherapy scanner such that we maximize radiation to the tumor and avoid any radiation to surrounding structures that we want to avoid. And then very finally, one of the things I think is very exciting is I'm collaborating with a startup company out of San Francisco to create a 3D mapping software for robotic surgeries. So this is a robot that can do needle-guided lung biopsies, and we take these X-ray images that are commonly acquired during these procedures and make 3D maps for the robot to follow in order to get down to the lesion. So just like the high-level summaries here is that learning to generalize from a finite set of data, especially the tiny data sets that we have in medicine, is very hard, if not impossible. But if you use patient-specific machine learning, you can overfit to the one patient who is about to undergo a procedure. And it turns out that in this case, overfitting isn't a bad thing at all. You overfit to the specific distribution, and you can really improve outcomes for a lot of very challenging surgeries. So with that, thank you. I'm happy to take any questions now or in the poster session.
So, I guess given this, how much data would you need to feel confident for a machine doing surgery on you right now? I guess, and as a quick follow-up to that, how close do you think we are to having this deployed in clinical settings at the moment?
Great question. So for me personally, as long as you have a CT of me, you're good to go. You can fine tune, like just use synthetic data generated from my CT, and then that's a model specifically for me as a patient, and I'd feel confident with that. The deployment question is very, very awesome. I think these two examples, so for fluid dynamics in pediatric neurosurgery and radiotherapy, these are maybe like a postdoc away from getting into like anything that like might be run on a scanner. But this robot is really cool because it's actually FDA cleared and has done about 1,000 procedures. And so right now, the implementation of our algorithm into the robot is still in testing phases, but I think maybe within a year, it might be rolled out in production, which is really exciting.
Thank you again so much, Vivek. I'll have our next speaker come on up. Well, I'm excited to also introduce our third speaker, Shirley Wu, who is a PhD candidate in computer science at Stanford, advised by Yuri Leskovich and James Zhao. Her work focuses on self-improvement and alignment in large language models and agents, enhancing their knowledge grounding, tool use, and ability to optimize multi-turn human-AI interactions. So excited to see how she's thinking about this as a collaborative experience for AI agents today. Welcome, Shirley.
Thanks for the intro, and I'm glad to be here presenting the talk, Building Collaborative and Human-centric Agents. So today's AI agents, they are powerful. They are able to use external tools, such as API calls, and they can take natural language instructions and just produce the actions for the task that you want. In my past work, we have built AI agents that retrieve knowledge. For example, give a user query. The agent is able to understand the user request, and they could retrieve relevant information from complex knowledge base and return the answer to the users. We also build AI agents that can effectively use tools. And those tools would be like API calls, for example, assessing the knowledge base, process information using embeddings, and visualize information and doing analysis. However, in all of these cases, it's usually a single-turn interaction, and there's no back and forth between the user and the AIs. Basically, the user give the agent task, and the agent give the user answers. However, the real-world tasks often involve human-AI collaboration. And particularly in these collaborations, it's up to the agent and the human to collaborate to complete tasks such as document editing, coding, mathematics, and scientific discovery tasks. However, to our disappointment, in these collaborations, the LLMs tend to jump to wrong conclusions very quickly. For example, if a user is asking, what's a good pasta recipe? The model will give very comprehensive instructions and ingredients, but all these generations might come to a waste if the user is a vegetarian and they don't eat chicken. So the model will need to generate again. In another case where the patient comes in and say, my muscle have been feeling really weak, the model might just give 6 different conditions that the user may or may not have, or may not understand. So in these cases, we see these AI agents, particularly large language models, they lead to very inefficient and sometimes useless conversation to the users. So the problems here are that the models don't naturally help users clarify the needs or explore different options. They are very passive, especially when faced with ambiguous user inputs, and they don't ask questions. So why would today's LM act like this way? We all know that the models are usually tuned based on single-turn human preference. And let's say I have a user asking, I want to write an article about optimism. Let's imagine there are 2 model responses. The first one is to give you a comprehensive article. And the second one is asking you a question. For example, how long is the article and what kind of tone do you want? If we only have one opportunity to interact with the model, it's very natural for us to prefer the first response than the second one, because at least the first response gives you an answer, but the second one, it doesn't really provide you with any answers. But asking questions would be helpful in the long term. So we see in this example, these single-turn rewards, they would encourage the model to generate the responses that might be informative in the short term, but may not be useful in the long term. So our work, Collab LLM, which received outstanding paper award in ICML this year, it empowers LLM to seek information from the users and collaborate more effectively with humans. The key insight here is simple. We want to reward the model responses, not just based on how helpful they are, but based on their long-term impact on the conversation. This is a reward mechanism we call a multi-turn aware reward. And here's two examples to show you how we did it. So let's say the key is we want to estimate the long-term impact for any model responses. And let's say here, the model provides you with an article. What Collab LM does is that it will generate synthetic conversation with a user simulator, which is another LM that we prompt to role-play the user. And this user simulator will continue the conversation. For example, the user simulator might say, the tone is too formal and the examples are too old school. And then the model will need to generate again. Maybe the user is not satisfied, and there will be these back and forth iterations between human and the LLM. So if we look at this future conversation, we see low efficiency, and maybe the user is not satisfied with the document, and the interaction experience is very bad. In another example, if the model asks you a question, like what kind of tone are you aiming for? In the future conversation, maybe the user provide more information, such as I'm aiming for an inspirational tone, and how you have with relationship. And if the model is being smart and good at collaborating, it might just generate an opening paragraph to see if the user like it, and even like provide some suggestions. So in this future conversation, it reaches high efficiency because you don't need to read the entire article. And you can get the document that you want, and this also leads to better interaction experience. So we see how the multi-turn aware reward changed the preference completely, where the first response that give you the article will receive lower reward because it's not that useful in the long term. But for the second one, it will receive higher reward. So by changing the reward design, we encourage the model responses that are useful in the long term, especially when collaborating with humans. In a nutshell, it composes of 3 parts. Basically, we want to sample future conversations, and so that we can provide you with evidence to look into how the future turns out. And we want to compute the reward based on this evidence, and use this reward signal to train the model, such that it would generate the responses that prioritize such long-term outcome. We see our model improve collaboration, and from a user study in our work, the users seem to agree that the base model, the AI seem to be over-agreeable. There's no debate or discussion. For base model with prompting, the AI seem to be very redundant and rigid, and ask the questions over and over again. For our model, the user says it helped really well on navigating what to say and what information is needed. It helped focusing on one part of the story at a time. And finally, it asks questions and makes you think of things that you never thought of. And I actually feel this is part of the point of why we need more collaborative AIs. It's not just tell you the answer that's out there in the world. It's also about how to eliciting the creativity from the human. So what's next? I think the high-level philosophy of Collab LM is to say, if you want things that work well with users, you need user interactions. You need to see how the future turns out to be. But we all know that getting real user interaction takes time, and sometimes real consequences. So if we want to be smart and we don't want to wait for a long time for those user interactions, we want to build a model of users. For example, if you want a blog that could, that's interesting to the users, you want those user feedback. But now, you may not want to send the blog to some of your friends and wait 1 week for their feedback. But if we have user models, you can get the feedback immediately. And we want to use this user model to enable more human-centric AI. And this is our ongoing work on building user simulators to evolve the real world. Starting from an entity, which could be a model, could be a person, or could be a company. They might propose some content instances, such as policy, post, or model responses. But instead of giving them to the real user, we want to give them to the user simulators. And those user simulators will provide you evaluation or interaction such that you can evolve those content instances. So I hope this brief introduction gives you a sense on what we've been doing. And in summary, we built Stark and Avatar that enable more intelligent AI agents that can retrieve and use tools properly. But in the real world, being collaborative matters. And that's why we built Collab LM, and it is a new way to define the longer lens and measure what matters in the human-AI collaboration. And finally, we are building user simulators that hopefully can lead to truly human-centric agents, and that could work well with you before you know it or try it. I want to thank my co-authors, and thanks for the invitation. Thanks, everyone, for being here today. Thank you.
Hi, Shirley. Thanks for the presentation. My question is collaborative ability is a subjective thing. So how do you know that you're doing it right? How do you know Collab LM is doing it right?
Yeah, good question. So in Collab LM, you know, in every task, there's an objective that matters to the user. For example, you want the task that's you want to do it as fast as possible, then you matter efficiency. You want to get good results, then you matter accuracy or whatever task metric. Or you matter, you think talking interactively with the AI agents is important, then you can matter this interactivity. So I think in every application, there are some metrics that matters to the user. But what Collab LM says is that you define the metric, and this metric can be applied to any future conversations. But now we want the model to generate those responses that can give you the best possible metric in these future conversations. So it's up to you to define the metrics that matter to you, but the Collab LM will optimize that for you. Yeah, thanks.
Hi, Shirley. I just want to ask about the multi-turn aware reward system. What is the difference between RLHF, which is reinforcement learning human feedback, with this multi-turn aware?
Yeah, great question. So I think RLHF is kind of fall into the single turn rewards. So basically what you usually see is in those benchmark is that you have users look at different, let's say 2 model responses, and you kind of choose which one work the best. It's usually happen before you know it, right? You look at the response, you kind of see, oh, which one might seem to be more useful for you. But however, it's not like the model response, you interact with the model for a few more turns, and you reflect which one will work well for you. So I think Collab LM is taking the post-hoc way. We want such evidence such that we are confident to say that, oh, this model response worked better, rather than relying on humans' subjective choices.
Sorry about that. So, okay then, yeah.
Yeah, thanks for the question.
Thank you.
Thank you.
Great talk.
So today, I'm excited to talk to you all about some of the work going on in our group. So our general approach to research is the following. In our group, we're really excited about the idea of developing machine learning and AI-enhanced simulation tools that let us ask very fundamental questions about the behavior of chemical and material systems. And what we're going to try to do with those fundamental insights is to either accelerate design and discovery of new materials or to identify more tunable or efficient synthesis routes to them. So to give you a tangible example of this, I want to talk about one of the longer-running research themes in my group that is focused on synthesis of carbon-based nanomaterials. So these are materials that we care about because they are of tremendous technological interest. They can be sort of coerced into exhibiting a near continuum of different mechanical and chemical and optoelectronic properties. And here I'm showing you an example of a few of these. So this is nanodiamond. These are graphitic nanoonions, so like concentric buckyballs. And this over here is a kind of agglomerate of nanoglass particles. And so, these particles are being touted for uses in everything from quantum computing to drug delivery, catalysis, and so on. But we're faced with this challenge. If we really want to integrate this into user-facing technologies, we need to be able to synthesize these materials in an efficient manner. And so if we take into inventory kind of the different approaches available to us, we find that they fall into one of two categories. We have low-pressure techniques, so things like chemical vapor deposition, that give exquisite control over the synthesis process. But here the challenge is the throughput. So we're talking microgram quantities of material per hour. On the other hand, we have these high-pressure techniques. So an example of this would be ball milling, or if I can be dramatic, detonation synthesis, that allows you to produce these particles in kilogram quantities in under a microsecond, so tremendous throughput. But as you might imagine, these are very difficult to tune. And so we became interested in this question of whether we could help design a new synthesis route that takes advantage of the pros of both techniques. So the throughput of these high pressure techniques and the tunability or the controllability of these low pressure methods. And so the method that we've been helping to develop is called laser shock synthesis. And the basic premise is the following. We are going to take a carbon-rich liquid precursor, and we are going to use a laser to impart an ultra-fast or a supersonic compressive shock wave in that sample. That shock wave drives the system to extreme conditions, thousands of Kelvin and tens of gigapascals, during which the carbon in that precursor phase separates out from everything else, and you form these liquid carbon particles. At some point, that shock wave passes through your sample, and you expand back down to ambient conditions, and that's going to drive a solidification that gives you one of the various allotropes of carbon. And so it's a really cool technique because this entire process can happen on picosecond to nanosecond timescales, and in principle, it's fully tunable. So my experimental colleagues have complete control over the shape of that laser pulse, which controls the conditions that you reach and the timescales that you dwell at those conditions. And it works. So here we go. This is an example of an agglomerate of, in this case, these are amorphous particles my experimental colleagues synthesized using this technique. But the problem is, again, we want to make this tunable. And so the fact that this is so efficient, it happens so quickly, is also a bit of an issue because it also means that experimentally characterizing what's happening during this process is practically intractable. And so there's all of these sort of fundamental questions about, well, how do the knobs that I'm tuning while running this synthesis experiment ultimately control the particles that I get out the other end? And so our group is using simulations to try to answer this, or to fill this knowledge gap. So how do we do this? So our sort of overarching research tool is going to be molecular dynamics simulations, and these are really nice because they work on a very simple premise. You're going to start off with a little bit of information about the system you're going to model, so this will be some initial coordinates for your particles, this can be like a crystal structure, and an interatomic model that describes how the energy of your system changes as you move your atoms around. Given this information, you can apply Newton's equations of motion to time integrate your system and predict how it's going to evolve in time. And that gives you quite literally movies of your system or simulation trajectories. And you can further analyze these trajectories to learn all sorts of things about your system, the equation of state, thermochemistry, dynamic response, and so on. And so it's a very simple but a very powerful research tool. So the difficulty here, though, is that the predictive power of this method is very strongly governed by the quality of this interatomic model, right? Any errors that we introduce here are going to propagate throughout the course of our simulations and can compromise the predictions that come out the other end. And so we spent a lot of time thinking about this question of how do we identify suitable models for our target applications, or if needed, to develop them. And so in particular for this synthesis problem that I presented to you all, really what we're trying to do with our simulations is predict the structure, dynamics, speciation, and kinetics of our systems as they evolve under extreme conditions. And in order to do this, we need our model to be able to do a few things. Describe chemistry, provide accurate predictions under high pressure, and so on. But equally important is the computational efficiency of these models, because the simulations that we're talking about are long and they involve many particles. And so I'm going to give you an example a little bit later on in this talk of a simulation of over 1 million atoms for about a nanosecond, and that simulation required over 1 trillion evaluations of our interatomic model. So again, computational efficiency is key here. So for the work that I'm talking about today, we kind of got started on this a number of years ago when machine learning and AI was just starting to be whispered in the sort of physical sciences. And so we really only had two choices available to us. We could use quantum-based approaches, which are very highly predictive, but here the challenge is that they're also computationally intensive. So we could simulate maybe a few hundred atoms for a few tens of picoseconds. On the other hand, we had what are called classical interatomic models. These are kind of empirical equations that are very computationally efficient, but they're not very accurate for these sorts of properties that we want to get right, and there's no clear route to systematically improving them. And so we became interested in this idea of using machine learning to bridge this gap, to try to get the predictive power of these quantum-based methods and the computational efficiency of these classical interatomic models. And so, at the time we started on this, there were maybe a couple of machine learning interatomic potentials here or there, but none of them were able to provide the computational efficiency that we needed. And so we went about developing our own, which we call CHIMES. And so CHIMES is a very compact, physics-informed machine learning interatomic model. So essentially, we're going to describe our total system energy through a many-body cluster expansion. So total energy comes from the sum over dimers and trimers and tetramers of atoms out to arbitrary bodiedness. And then we're going to use this generating function to write down what each one of those n-body terms is. And so this is just telling you two things. We're using Chebyshev polynomials as our basis functions, and when we need to create basis functions for many-body interactions, we basically do it through a tensor product. And so in the language of machine learning interatomic models, we are a parametrically linear descriptor-based model, and our descriptor is the fully connected graph between the atoms that comprise each one of these n-body clusters. So for a simple two-body interaction, you just get an expression like the following. So each t is one of our polynomials. We plug into it the distance between the two atoms that we're trying to evaluate energy for. And when we train our model, what we're doing is fitting these coefficients that live in front of each one of these polynomials. These models are trained on data that come from quantum-based simulations. So you'll get a set of snapshots of what your system looks like, and you'll use the quantum mechanics to label the forces, energies, and stresses for that system. And when you're training your model, you're basically trying to say, well, given the same configuration, CHIMES, can you give me the same prediction? And so, looking at this, again, this is a very simplistic model. And so practically, this means that these models use order of magnitude fewer parameters than the other ML potentials out there on the market. And so practically, that means that we need orders of magnitude less training data, and these models are very computationally efficient. But we're able to do this without meaningfully compromising on the accuracy of the predictions that we're making. And so as an example of this, this is just an excerpt of some data from a recent model that we published for carbon that works from ambient conditions to about 10,000 Kelvin and 100 gigapascals. And it is currently the most accurate and the most efficient machine learning interatomic model on the market. So tiny but powerful. All right. So this computational efficiency turns out to be very important. So to remind you, why are we even worried about this right now? Again, we want to be able to help our experimental colleagues understand how these particles formed given the controls that they used during their synthesis experiments. And using our CHIMES models, we can actually simulate this process with atomic resolution on the same scales as the experiment. So each little red dot you see in here is an oxygen atom, and these spheres you see forming, these are the carbon nanoparticles that are synthesized through this process. And so again, we're finally able to fill that knowledge gap. Again, this is a simulation of over 1 million atoms, so a trillion evaluations of our ML potential went into making this. Just to sort of orient you guys, before developing our model, we would have been stuck with a quantum-based simulation, and that's how big our simulation could have been, which would have precluded seeing formation of even a single nanoparticle. So again, these are really powerful tools. So I want to switch gears now. So far I've kind of painted a really rosy picture, right? We develop these potentials, they solve all of our problems for us, everything is wonderful. Now I want to spend some time on what is perhaps the darker side of things. So increasingly, these tools are being adopted by the simulation community, and those of us that develop these tools, of course, want others to use it, and so we are releasing our open source software and our model development frameworks. And practically, this means that anyone can bring their training set and plug it into one of these tools and get out a model. So making models is easy. The problem is making good models is not. And so what I'm going to do in the next couple of slides is give some examples of some of the challenges that one faces and some of how our framework and some of the tools that we're developing can help to meet those challenges. So challenge number one, how do we know if our ground truth is good enough? So when we train our models, we are training them on data from quantum-based calculations. And of course, these are data-driven models. So if a model doesn't work, is my training set not complete? Is it something to do with my hyperparameters? For practical reasons, we cannot use full quantum mechanics when we are training these models, right? We can really only do that for the hydrogen atom. So is the approximate version of quantum mechanics that we're using suitable for their application? Well, how do I answer that question if I can't use the quantum mechanics to actually make the prediction I'm trying to train my model to predict? So to give you an example of this, if you kind of take inventory of the literature right now, you can find a handful of ML potentials that are designed to work for silicon. They all claim to be quantum accurate. And if you ask these models, okay, cool, what's the melting point? They all get it wrong. In this case, by about 300 to 250 Kelvin. So you can see that over here. Here's a phase diagram. The gray is experiment. The red is these ML potentials. And so again, we have this question, okay, but why are these wrong? Well, it turns out if you ask, okay, well, what data labeling method are you using? What ground truth are you using? They are all using the same approximate quantum-based method. So this is called DFT, density functional theory with a GGA functional. So why are they all using the same approximation? Well, these models are all computationally expensive. These are big models. And so they require training sets on the order of 10,000 to 100,000 configurations, which might not sound big to some of you, depending on the space you work in. But remember that each one of those training points needs to be labeled with a quantum-based method. And so if we ask, well, what is the computational expense of doing one of those calculations? You can see the functionals that they're using, the approximations that they're using, allow you to make these calculations in just a couple of minutes. But as you go up to increasingly accurate methods, those minutes become hours. And so practically, this means they cannot ask the question, well, what would have happened if I trained my model on this method instead? Would my phase diagram be better? Well, it turns out, if you recall, our models are compact, which means we don't need as much training data. So for this application, we can get away with about 500 to 1,000 configurations. And so we can actually go and train our model on the same data set labeled with different approximate quantum methods. And we can ask, okay, well, which one of these would have given us the right answer? And if none of them do, perhaps that tells us it's something else, the training set completeness or the model hyperparameters. So what does this look like? So here is our experimental phase diagram. The points are actual experimental measurements. Okay, so in any case, here is the experimental phase diagram. When we train our model on these two GGA functionals, we end up with curves that land right about here, which is consistent with the predictions the other models make. When we move up to these higher rung methods, so this meta-GGA and this hybrid, what we find is that our data fall perfectly on these experimental data, and we took our calculations and expanded them out for the rest of the phase diagram, and they pretty much land right on top of the experimental data for all of these. Take my word for it. So practically what this tells us is that the DFT, or the quantum-based method that this community has by and large said, yeah, that's pretty much good enough, is really one of the problems in the accuracy of our predictions. All right, so let's switch to challenge number 2. All right, so how do we know when we're done training? So in the early days, development of these ML potentials was pretty much constrained to expert users, subject matter experts in both the training of the potentials, but also the future application of those potentials. Nowadays, those of us that develop these tools tend to ship them with something like an active learning framework that tries to automate this process in some way. The basic premise is we're going to start out with some training set. We're going to develop a model to that training set, and we're going to simulate with it. And we're going to ask, okay, is that simulation good or bad? Is the model good or bad? If the model's bad, we're going to try to have it learn from its mistakes. So we're going to take some of the configurations that are generated by our model, and we are going to filter them, try to find those information-rich configurations, label them using our ground truth method, add them to our training set, and kind of crank through this until the level, or until our accuracy is what we want. And so most of these steps are super easy to automate, but there is some decision-making that goes into these two steps. So it turns out that these two steps are two sides of the same coin. If I am trying to decide whether or not my model is good enough, and I don't really have a sense of, well, what is good enough for my physical property, for example, that I'm trying to validate against, we can ask these questions in terms of the training data. So let's say I'm running a quantum-based simulation, and it gives me some configurations that live in this space, and I'm trying to generate a model that is going to give me the same distribution of configurations back. Well, if I generate two models and one's giving me stuff that looks like this, that's probably a good model, and if it's giving me stuff that looks like that, it's probably a bad model. Conversely, now if I want to select information-rich configurations to add back to my training set, well, I'm probably going to want stuff that looks like B because I don't have that in my training set already instead of A. So intuitively, it's pretty obvious what we're trying to do, but automating this in a quantitative way turns out to be very difficult because the data objects that we're trying to perform this operation on are 3n dimensional, where n is the number of atoms in our system. And so in order to be able to do this, we need some compact way to describe what does one of these configurations look like. And so we developed this cluster graph fingerprinting method to help with this. I'm not going to talk through what is going on here exactly, but suffice it to say that we're able to take one of these configurations and essentially in a low-dimensional way say, here is what this configuration looks like. And so now that we have this way of representing these training configurations, we can start to ask some questions about, well, how novel is this configuration given some other configurations? So let's see an example of this. So, okay, let's say that we are trying to train a model, and again, we want our model to give us back the same distribution of structures that is generated by our ground truth method. Well, we can now create that distribution through our fingerprints, and we can ask, using things like the Mahalanobis distance, well, are these two distributions indistinguishable from one another, in which case that's a good model, or are they distinguishable from one another, which means my model is making bad predictions? So basically assessing things that look like this. And so what we're going to do is integrate this into our active learning framework. And in doing so, once we find that those two distributions overlap, we can say, OK, our training task is done, and then quit. And this removes the need for subject matter expertise in this training process. So here's what this looks like. In this case, we are training a model to work at multiple different temperature pressure state points. In any one of these plots, this y-axis is that distinguishability metric. And any number that falls into this red region is saying that the two distributions I'm comparing are distinct, that's bad, and anything in white, that's good. This first bar here is just the ground truth distribution. So this bar is basically saying, given this distribution, on average, how far is any fingerprint from the population mean? But what we're going to do is train a model on this data point, and we're going to say, OK, now, given that model, how much different is its distribution from the ground truth? And you can see we're into the red. That's a bad model. And we kind of keep going through different active learning cycles and until eventually you can see that by that last cycle, all of these distribution means are falling in the indistinguishable region. And so again, that tells us that our training task is done. And so again, by integrating these sorts of capabilities into our framework, our hope is that we're making things easier for others and we're helping to overcome some of the limitations that exist due to use of kind of just off-the-shelf strategies for generating these models. And so with that, I'm going to thank my students who are doing all of the heavy lifting here, our funding, primarily through the Department of Energy and the Graduate Fellowship Research Program. Got that backwards. My collaborators at Lawrence Livermore National Lab that were involved in the shock synthesis work. And then I'll just note, again, we developed these tools for the community. So if you're interested in using these, please check them out on GitHub. And with that, I would be more than happy to answer any questions.
So that was a great talk. I really enjoyed thinking about the ways in which this machine learning, these techniques are being integrated. And the active learning piece at the end really struck me. One of the things I was thinking about here is the way that you're trying to search through the problem space is using this simulation data. And I was curious, did you ever see that there's a need actually to go back to the physical experiments themselves, or can you get away? Like, does the ability, your really fast sampling ability allow you to expand the frontier of modeling that you can actually say, well, we don't know enough, but we need some sort of ground truth here because even the quantum simulator isn't accurate enough?
Yeah, that's a good question. So I think that from the training perspective, it would be wonderful if we could use experimental information to guide, let's say, the sampling. It turns out that's not a really easy thing to do, though, simply due to the resolution of the experiments. And so instead, we play games with how we run our simulations that generate the data, so bias sampling methods and things of that nature.